Good afternoon, good evening, everybody. My name is Corey Oses. I'm a postdoc here at Duke, and today I'm going to be presenting on the general topic today is on thermodynamics. We're going to be covering two modules. That's the AFLOW-CHULL, which stands for AFLOW-CONVEX-HALL module, and then the latter part of the talk, which was written by Dr. Rico Friedrich, is an important correction that we'll be discussing, which is AFLOW-CCE, coordination corrected enthalpies. Okay, so let's jump right in. Okay, so get this out of the way because I can't see. All right, so the question that we're looking to answer today is an important one, and that is the question of whether a material is going to form. There are two controls or let's say regimes under which we're going to look at this problem or analyze this problem, or you can look at this problem. This is a reaction pathway. So you can see here that we start off with particular reactants. Okay, so let's say pure component A, pure component B, and we try to mix them together. The reaction is going to follow some sort of pathway. You can see here that, so the y-axis here is the energy. It's going to realize some sort of transition state. Okay, so depending on which pathway is followed, you can realize one transition state or another. There's going to be another one here. And then ultimately, you're going to get some products at the end after everything is settled. Okay, so if we imagine that the system, has some sort of temperature, there's a given fixed amount of energy in the system. And this energy for the system sits at this point here, okay, then we understand that the product that's going to form is product one, because the product two requires too much energy here. Okay, so there's not enough energy in the system to realize transition state two. This is understanding the full reaction pathway here, including the transition state. This is really an understanding of the kinetic processes that are driving the reaction. On the other hand, if we sort of close our eyes, okay, and we just look at the reactants, the difference of the energies between the reactants and the products, you see that product two ultimately has lower energy, okay? And so therefore, if we just ignore all the transition states in the middle, the idea here is that if we're under thermodynamic control, product two is going to form, okay? Ultimately, obviously, both effects are very important and we need to analyze both, but for the purposes of this talk, we're just going to be looking at thermodynamic control. Okay, we're just going to focus on this piece of it. Just what are the reactants and what are the products, and how can I analyze the energetics of the two? So the question here is, does a mixture, okay, so now I've given labels to this mixture. I have a mixture of palladium, platinum. Does this mixture want to stay mixed, or is it going to decompose into its components, pure palladium and pure platinum? Okay, so this is really a question of the energetics of the reaction. We're going to be looking at the Gibbs free energy, which has the controls of temperature and pressure, which is what we can control in experiment very easily. And there are two fundamental factors here. We have the enthalpy and then the entropy term. Entropy term, which is multiplied by the temperature. And really, these should be delta H and delta S, right? Because we're looking at the differences of the enthalpy and the differences of the entropy. And so if a particular reaction, in this case, a decomposition reaction, is favorable, then the reaction needs to be, well, first of all, it needs to be spontaneous, so it needs to be less than zero. Okay, so there needs to be energy that's released. And one way to do this is, well, there's a corollary here, right? So we want to minimize the energy, so we can minimize the enthalpy, and we can also, at the same time, we can maximize the entropy. Okay, both have the effects of reducing the overall Gibbs free energy. For the purposes of this talk, we're just going to focus on the enthalpic contributions, okay? So we're looking at enthalpic optimization and what are the contributions to the enthalpy that stabilize a material. By the way, if I didn't mention it earlier, if you have any questions at all, feel free to interrupt me. It's good that we get the questions at the time when you have them. So, okay, so let's look at how we calculate the enthalpy of a material. What does the enthalpy mean? So if we have this mixture here, this palladium platinum mixture, enthalpy has two terms to it. So we have the internal energy, and then we have a term that is the pressure volume term. For the purpose of this talk, we're going to ignore pressure. We're going to assume that there's no pressure on the system. So let's talk about the internal energy. One way that you can analyze the internal energy is you could break up the internal energy by different terms. Okay, so you can imagine that we can look at the internal energy as a series where the first term is the energy of all of the components by themselves. Okay, so what is the energy of having a particular number of palladium atoms, a particular number of platinum atoms? Then we can look at interactions between these terms. Okay, so the fact that palladium is bonded to platinum in a particular area, that they're nearest neighbors, this is going to give a particular contribution to the enthalpy. Next nearest neighbors and neighbors beyond that, that's going to be order different terms in this factor here. Okay, and then we can look at third order terms. We get more complicated. So now we look at three body interactions. Okay, where we look at not just what's bonded to each other pairwise, but triplets. What is the angle between them? All of these are going to have effects on how the overall energy of the system looks like. And so this is one way of looking at the enthalpy and breaking it up. So for the purposes of this talk, I'm going to mention that the way we calculate enthalpy is called density functional theory. Okay, so we understand the enthalpy from the level of quantum mechanics and electronic density. Okay, we didn't have a talk to discuss what density functional theory is, where it comes from, how to do it. And you're welcome to treat it as a black box. Okay, so the idea here is that we can take a structure, we can input it to this code, and we get back an enthalpy. Okay, this enthalpy is at zero pressure and zero temperature. It's the ground state enthalpy. So we can take our three materials here, the three compounds, the mixture, and then the two pure components, and we can calculate their enthalpies and analyze the differences. Okay, but we're going to do an important trick here, and we're going to sort of renormalize or rescale the equation here. So we're going to take the enthalpies of the pure components and we're going to zero them out. And what that gives us is what's called the enthalpy of formation. Okay, so we take the enthalpy of formation of our mixture here, it's going to be the enthalpy of our original system minus the compositional weighted enthalpies of the pure components. Okay, you're going to realize why that's important in the next plot, but just understand that the enthalpy of formation is a useful way of renormalizing the enthalpies of this reaction. So here we have a plot. We're going to visualize thermodynamic stability. So we have a plot here where we have the energy of the system on the y-axis, the formation enthalpy, as I discussed it earlier. And then on the x-axis here, we have the concentration spectrum. Okay, so we can have pure palladium here on the left, pure platinum on the right, and then mixtures in the middle. We have three components, the pure A, pure B, and then the mixture, the 50-50 mixture here. And you can see why the enthalpy of formation is useful. Because if we zero out the enthalpies of the pure components, then the pure components are going to be zero in this plot. Okay. And of course, that's going to shift. It has what it basically does is it tilts the overall the raw enthalpies of the system so that we get the pure components exactly at zero. So now let's look at this. So we have the 50-50 mixture. The fact that the 50-50 mixture is below the tie line connecting the pure components tells me that this reaction is spontaneous, that this reaction is preferred. So the mixture is going to want to stay a mixture over decomposing into its pure components because it's lower in energy. Okay, so this is the difference of energies. This distance here, this energetic distance, this is actually the driving force for this reaction. Okay, we'll talk a little bit about that in a bit. But in order to understand stability, we need to not only understand stability from the perspective of does this want to decompose into its pure components, but there are many other decomposition reactions that are possible. Okay, so we need to analyze decomposition with respect to other compositions. Okay, so we can look at a mixture here which has more palladium than platinum, and even different arrangement of atoms. Okay, there's a lot of different ways that the system can decompose. We want to understand, is the system globally stable? And so what we're going to do is we need to perform this tie line analysis for all of the different combinations on the plot here. Okay, and it's actually it boils down to a very common or simple analysis mathematically, we really want to find out the outermost points on this plot. Okay, so those are going to be the most stable. Well, give me a second because I see that there is a question. Previous equation, left-hand side and right-hand side, first terms are the same. Enthalpy of mixture equations. Let's see, did I make a mistake on the plot? Which slide were you referring to?
I think slide 11. It's not the same, but it's an important subtlety to point out.
Yes, okay, so it looks like, so you might notice that there's the enthalpy of formation here. So slide 11, the left-hand side, so with the enthalpy of formation here is equal to the raw enthalpy of palladium platinum, okay? Minus the raw enthalpies of the pure system, pure A and pure B, which are compositionally weighted. Do you see how there's a distinction between the enthalpy of formation versus the raw enthalpies? It's not exactly the same. Okay, good. Happy to hear. It's an important distinction. So, and it's subtle. It is subtle. Okay, so we want to do an analysis of global stability. Okay, which materials are going to form if I put a particular mixture of components together? This is called the convex hull. And the convex hull, you can imagine, we take a giant rubber band and we wrap it around the data that we have here, and the points that the rubber band touches are the most stable points. Okay, so let's dig into a little bit more of the analysis here. The edges of this convex hull, the tie lines, these constitute what are called two-phase equilibrium. Okay, so if we try to mix this system with this system, they're going to happily coexist. They're not going to want to mix together. Okay, so they're going to coexist together. That's what two-phase equilibrium is. Meanwhile, systems that are off the hull, okay, so anything above it is going to decompose. So let's take, for example, this system here, PD2, PT3. Just from the visualization, I can tell you what the decomposition reaction is going to look like. So I take PD2, PT3, and I immediately just drop straight down vertically, and I look at the tie line that is directly below it. The points that are the edges of the tie line, those are going to be the other terms in the decomposition reaction, okay? And we can balance the reaction, okay? We can do that. That's simple, just balancing the components of the system. That's mathematics. But so the idea here is that we can actually figure out what the system is going to decompose into. And this distance, okay, this energetic distance, the distance here to here, this is actually the driving force for that reaction, okay? So if that distance is very large, then there's going to be a very large propensity for forming the reactants, okay? So that's a very large propensity for decomposing. But you can see here that the distance is not that big, okay? 3 MeV per atom is not that big. And big here is in terms of room temperature excitations, okay? So remember, all of these calculations were performed at 0 temperature, okay? A lot of these reactions, if we're doing this in experiment, they're going to be done at room temperature. This is a factor which tells us what are the thermal excitations that occur at room temperature. Okay, we put 300 Kelvin here. This is the room temperature excitations. So this term is pretty small compared to room temperature excitations. So you can think of this as sort of an error for our analysis, okay? If it's less than 25 MeV per atom, it's possible that this is stabilized through, let's say, entropic effects at room temperature. Okay, so we've implemented.
Please let me ask a question.
Sure.
So the slide you just showed, yeah. So if I take a particular concentration, a particular value of X, there are many entries vertically, right?
Yes.
So these entries correspond to what? Random?
Yes, it's a good question. So these correspond to different, okay, so if we're looking at a particular line of concentrations, that they all have the same concentration, but they're going to be different atomic arrangements. So you can see here how the atoms here, there's a plane here of the same atoms, but here we have a different arrangement of the atoms. So that's going to give me a different energy. Okay.
Okay.
So we need to look at all different combinations, not only changing the composition, but also changing how the atoms are arranged in the structure. It's a good question.
Okay. Wait, so for each concentration, the lowest energy of formation. How do you know this is the configuration that's lowest? How do you know that that you don't have another configuration just below that?
You broke up a little bit, but I think I understood the nature of your question, and it's actually a very important one. You said, how do we know that this is the minimum energy structure and it's not a structure that we haven't explored, let's say, right?
Yeah, exactly. Especially for, say, at any concentration. So the envelope outside, how do you know there's no other point lower than that?
Yeah, this is a very good question. And the truth is that, you need, the truth comes down to statistics, okay? So the point is that when we do this analysis, we need to be certain that well, there's no way to be absolutely certain, but we need to sample a good amount of the space, okay? And there's particular configurations that it's more than likely that these configurations are going to appear in the convex hull. So for example, if you know that particular configurations exist in experiments, they've been experimentally validated. Okay, so you know that these compositions and these arrangements, these structures actually exist. There's a good chance that these structures are going to be the minimum on this convex hull. So you want to sample those structures. But the truth is that that if you don't sample the minimum energy structure, you don't know that this convex hull is incomplete. We rely on statistics to make that analysis.
Okay. Thanks. Yeah.
Sure. Okay. So we've implemented this analysis in AFLOW. It's called AFLOW-CHULL. And I just want to briefly mention that we do a bit of data curation. It's important because for example, we do a very good job of, or we do our best to try to maintain a database where all of the configurations, all of the calculations are done consistently, and that they're well converged, etc. But you can imagine that if you're pulling from a lot of different sources, it's possible that you encounter an outlier where that outlier either was not calculated with the same parameters as the others, or it's not well converged. Okay, and so the AFLOW-CHULL analysis will actually detect these outliers and remove them. Okay, it does what's called the Q test. It's a very simple test, and it'll remove extrema, let's say, which are probably not data that belong on this plot. They're not. It's not a homogeneous set of data. The other implementation or function that we do that's very important is that we actually perform an analysis of which structures are duplicates. Okay, so for instance, some of the data that we pull is from the inorganic crystallographic structure database, and within that database there are many duplicates. And so you can imagine that if I have a bunch of duplicates, each with a little bit of different energy, that's going to change my analysis of the distance to the hull, and so on and so forth. And so it's important to figure out which structures are really unique and which ones are equivalent. And so we do that analysis automatically. It's built in, this analysis into AFLOW-CHULL. This is referencing the talk yesterday that Dr. Oses gave. Okay, so we actually have a web application where you can visualize these 3D structures. Okay, so it's a great tool for teaching, and I'm going to ask that everybody go to AFLOW.org/AFLOW-CHULL. I'll navigate there with you, and we're going to go to a particular convex hull, but we'll do that together. So let me close this out. I'm going to stop sharing real quick, and I'm going to share my full screen so that we can navigate together. 1 second. Stop sharing. And I'm going to share my screen. Yes. Okay. Can you guys see my browser here? DuckDuckGo?
Yes.
Okay, good. All right. So let me reorganize this a little bit so that we can see everything better. Okay. So we're going to navigate to AFLOW.org together. Okay. AFLOW.org. And then with me, you're going to scroll down to this button, AFLOW-CHULL. Okay, this is how we're going to get there. It's going to open up another tab. I'll give everybody a few seconds to navigate there. Okay, so what we're going to do here is, you see we got a full periodic table. You can click on the elements that you're interested in building here, but we're going to do that. We can also type in the values, so I'm going to do that. We're going to go to one convex hull together, so we can see together how it works. So we're going to go to silver, gold, cadmium. Okay, so we'll type that in. We're going to hit enter.
Sorry, please, could you put it in the chat?
Yeah, absolutely.
Okay, thank you.
You should also be able to see the composition here on my screen, but I'll do this here. Okay. All right, I'll give everyone a few seconds just to navigate there. And in a few seconds, once you hit enter, you should see a plot like this one, okay? Now you'll notice that we don't have two components like I've been showing earlier, but now we have three components, okay? And so instead of tie lines, you're gonna see tie surfaces. And you can take your mouse, and by clicking on it, you can actually pan around, zoom in. You should be able to zoom in with your mouse and actually analyze what the surface looks like. Yeah, the link may not be as identical. You can see that our links are a little different because this is actually a session which saves some of the data that we have, and so your particular URL is going to be unique. But thank you for sharing the link.
Oh, okay.
Right. So so here you see that instead of having two components where we have our tie lines, we're now going to have tie surfaces. So let's look together what's going on. So we have a bunch of points that sit on top of the convex hull, and then we have a few points which actually define it. Okay, so they define what the surfaces are connected to, or how the surfaces are defined. So let's take a look here. So remember, I showed you earlier that we have this distance to the hull, and this distance now can actually be, okay, so this point here sits right on top of this tie line, okay? So you can see here that if this point, the decomposition reaction is going to consist of these two phases here, okay? So you can actually see that visually on the 3D hull. If I click somewhere else, now we see that you can not only are we decomposing, we're not going to decompose just into two components, but you can actually decompose into three, okay? And now we need to fit in that, calculating that distance is a little more challenging, right? But you can see here how that looks, all right? So analyzing that respective distance is very important, okay? So this is just a way of visualizing what I mean by the distance to the hull and what these decomposition reaction pathways are going to look like. So let's see, if I click here, it's possible that it's a little frozen. Yeah, it's a little frozen. So I'm going to hit reset. Okay, so what I'm going to do is I'm going to show you a little bit about how this app works. You're going to click on highlight hull points on the left. Okay, and you're going to see that it's going to highlight all the points that define the convex hull. And you actually get that list populated here on the left. Click on one of them. Okay, it's going to switch you to another screen. And if you give it a few seconds, it's going to populate a bunch of cards. All of these cards are giving more information about these points. So you can see here that we have the composition, the compound. We have the AUID. Okay, so what is the entry in our database? It tells you that it's a ground state system. I highlighted all the hull points, so these are ground states. Gives you some information, just some relevant information about the structure itself. Okay, the prototype, the lattice, the energy density, the formation enthalpy, distance to the hull. If you want more information, you click on more info, and it's going to open up another tab where it takes you to the web page of that compound. Okay, what I like to say is that this is the Facebook page for this compound where we get the picture and then more information about the material. And you get all the information that we calculate for it. So this is it's a very interactive web application where you can really do some very deep analysis of what the convex hull looks like and what are the points. So you can do that for all these points here. And then when you're done, click on the little hull symbol at the top right, which is called selected hull. And we're going to return back to our original picture. Okay. So one thing I'm going to point out is that so interacting with the web app is useful, but let's say you actually want to do a more thorough analysis. One of the things that I recommend you do is you click download PDF. Okay. So we're going to click on download PDF. And it should download a PDF to your to your downloads folder, or however your system works. Go ahead and take a second to open that up. Okay, so you should get a picture like this. The first page is an illustration of the convex hull. It's the same illustration of the convex hull, but we're just looking at it from this perspective, right? Just from the top. And where the distance is, okay, the depth is illustrated by colors. Okay, so you can see what the convex hull points are and what are the depths. If you scroll down, this is going to give you a big report of all of the compositions, the entries from our database that were used to calculate this analysis, this convex hull. So let's take a look at what we have here. So it's sorted by ternaries at the top. Okay, so systems that are in the middle here that have 3 phases, and then the binaries are going to come next, and then finally the unaries. So it's going to go in descending order in terms of chemical complexity. And you can see that the first entry here, this system is unstable. Okay, so it sits somewhere on top of the hull. You see what the prototype is. By the way, this is a link. So if you click on this, it's going to take you to the entry page for that system. Okay, so we have a bunch of links. I'm going to go back. Okay, so you get the prototype, you get the AUID, some information about the space group, the spin, the enthalpy of formation. Then I'm going to point out the last entry here. This is the distance to the hull, so 162. Remember, relative to room temperature, 25 MeV, room temperature fluctuations, this is a very large number. What we get with unstable systems, we also get the full decomposition reaction. Okay, so this system is going to want to decompose into pure silver and then some sort of ternary here. Okay. Now, for systems that are ground states, you'll actually see them easily by eye because they're highlighted in green. Okay, and this is actually sorted by the distance to the hull. So it's as if we're tracing the compositions from the one that is closest to the hull all the way to the top. And you'll see that we have one highlighted in green. This is the one that is at the bottom, the one that forms the convex hull. And then we have a few in orange. These systems in orange turn out they have the same space group as the system that is on the convex hull. So in some sense, these systems might be structurally similar. It's just for us to point out that these systems might be of interest to look at. We highlight a few other properties here. This is called the stability criteria, and I haven't talked about it yet. But when I do, you'll notice that it's listed right here. And then we get the N+1 enthalpy gain. Again, I haven't talked about these 2 properties just yet, but they're listed here. The vertex of facets here, the 3-phase equilibrium. So what am I showing here? So this is a list of all of the phases that are connected to the triangle. So let me show you what I mean. If I'm at this point of the report, what I'm listing are all of the compounds which touch, which are connected by a line here. Okay, they're connected topologically here in the convex hull to the point of interest. Okay, so these are the vertices that are connected to this system. Okay, so it lists all of these connections. Okay, so we can get a sense of the topology without actually looking at the image. And I'll show you in a bit why that analysis has been important for us. Okay, are there any questions so far about this page? The last thing I'm just going to point out is that this is, again, there's a bunch of internal links, anchors that are important here. So if you go to the picture here, I want to see what the report is for this, or the table is for this composition. I just click there and it's a link and it takes me to that part of the report. There are other links embedded in the link in the PDF. If you see here, you can click on all these links. It's going to take you to those parts of the PDF and you can do those and you can look at those compositions there. Okay. You see here for this compound that we actually have 2 highlighted in green because these systems are actually duplicates, okay, despite the fact that there is a little bit of difference in their energies. Okay, this is just numerical noise. Any questions? If not, we're going to go back to the slides. Let me stop sharing and I'm going to pick up with the slides here.
So I have a quick question, sorry. How well do these results match experiments?
Yeah, it's a great question. We have a number of papers where we validated a number of alloy systems. So
Okay.
I'd be happy to send you some of those compositions, but I would say that we span a lot of we've spanned virtually all of the intermetallic binaries very well in terms of prototypes. Those are well converged. The ternaries, we've also spanned a number of different prototypes, although as you increase in dimensionality, there's just more ways that you can make combinations, more ways you can create decorations. But we've done a number of analyses for various alloy systems, and it shows that these are well converged. What I will say is that this is the power of a database, that we can validate these various alloy systems over a course of many publications, and we recycle this data over and over again. So we validated this alloy system. Let's say we validate the silver gold system here. Well, we know that piece of this now ternary system is well converged. And so by having a database that we can continue to recycle these systems, you only continue to build on top of those validations. So a number of these systems, and again, we've also spanned a number of known experimental systems that we know are going to be either the points on the hull or very close to the hull.
Okay, yeah, thank you. Yeah.
Sure.
I can add just a quick comment. There's of course also the caveat that we can never be more accurate than density functional theory. So if density functional theory gives us bad results, then there's not much we can do about it.
Well,
Corey will actually talk about it later on.
Sure.
About what we can, there's some things we can do about it, but yeah, DFT is the limiting factor here.
Right. Yeah. So okay. So the next piece that I want to talk. So I talked about these three-phase equilibria, right? These points that are connected on the convex hull to the point of interest. Why would we be interested in such data? So we did an analysis of superalloys. Okay, and a number of these superalloys are hardened through a temperature treatment. Okay, so let's look at, is this called age hardening? Okay, so we look at a system here, an aluminum copper system. Okay, the host matrix there's really a lot of aluminum and there's a bit of copper in the system, and we can perform a particular heat treatment. Okay, so we increase the temperature very rapidly, decrease the temperature rapidly. This is called quenching, and then we do an annealing at a lower temperature. This is going to result in the formation of precipitates. So in the middle here, we're going to get, you can think of them as like nuts in your brownie, right? Something like that, where you get these little pieces where inside of the host matrix, the greater host matrix, which has a composition of earlier, this aluminum copper system, we get another phase, okay, which in this case looks like it's more copper than aluminum, this precipitate. Now, these precipitates are important because they actually prevent the motion of dislocations, which hardens the material, okay? But so if we're looking at a number of different compositions and we want to see which superalloys will lend themselves well to age hardening, we need to know if the host matrix can be in equilibrium with the precipitate. Okay, so let's say we have a range of compositions over which we can have this precipitate exist. Okay, if we want the system to be in thermodynamic equilibrium with the host matrix, we can have a boundary which crosses here in this side. So we need to have some piece here of this tie line here, which can access this top point here. You can see here that if I have a tie line which crosses this boundary here like this, I still have a range of compositions here where there could be a tie line that connects between the composition of interest and the host matrix, the pure aluminum. However, if the topology of the convex hull is such that I actually have a tie line here, you can see that there exists no compositions where there's going to be a tie line that connects between the red and this top line here. So this is a way of screening compositions of interest for the superalloys. And we did this analysis in 2017. This was part of our way of screening through different superalloys. And we made a number of predictions. And in 2018, an experimental group independently verified some of our predictions. I see we have a chat here. A powerful material design tool. Now going to the lab, is there any way to decide the appropriate synthesis protocol for the results to match? The synthesis pathway is very important here because it's a difficult question, because you're right to say that the synthesis pathway is going to affect the phases that I'm going to realize ultimately. There are some synthesis pathways where if we quench, for instance, we can actually achieve non-equilibrium states, okay? And how long this equilibrium state lasts, it depends on the material, on the kinetics of the material. So this analysis is in a sense a bit independent of our synthesis pathway, but it's important to realize that that is an important component, the kinetics of the system. This is a bit outside of the thermodynamics. However, if we allow the system to realize its ultimate thermodynamic state, the minimum energy state, these results would be the ones we would expect. So your question is more involved with the kinetics of the system. I hope that
as a former experimentalist,
thank you.
Computation will probably not be able to provide a great synthesis pathway in a really long time, as Corey mentioned. These are just the ones that experimentalists should look at if they want to have a higher likelihood of succeeding forming a compound. How to make them is a very, very different question, and would be great if we could provide the answer to that, but I don't think science and computational science is still far away from actually achieving that. Molecular science is much closer to that answer.
Okay, so we see another question, whether AFLOW-CHULL phase diagram provide properties or thermodynamic properties, or what are uses of AFLOW-CHULL chosen phases? Yes, remember when I talked about this analysis in the beginning, I said that we were not going to be doing an analysis of the kinetics, right? So we were going to be avoiding, at least for this talk, right? There are ways of doing this analysis and understanding entropic effects, kinetic effects, and so on. But for this particular analysis, we're going to be focusing on thermodynamic properties. Okay, so if the system is allowed to achieve ergodicity, right, where it samples all of the states in the system and finds the minimum energy system, these are the results we expect. But of course, kinetics can interfere with that search, that ergodic search. Okay, no problem. All right, so let's keep going. Okay, so that's one way of using the data that we have. One example of how we use this data from the convex. So this is another one. We've created a descriptor that's called the stability criterion. So okay, I talked about the distance from the hull from the perspective of the top. So if I have a system that's going to decompose, there's going to be a particular distance down to the bottom of the convex hull, and then that driving force is that distance, right? But now what if I want to ask the question similar to what was asked earlier, how stable are the points on the convex hull? Okay, so what is the likelihood in some sense that this point is really the true stable point and that there doesn't exist another point that maybe we haven't realized? So we can do an analysis where we actually figure out what is how robust is this material in terms of being the stable composition. So what we do is we do sort of a perturbation here. We take this system, okay, let's say we're doing an analysis of this system, we remove it from the convex hull, recalculate what the new convex hull looks like without this system, and then calculate that distance from the true convex hull. So this is called the stability criterion, okay? And in some sense, I think this really goes to the previous question. This gives us an idea that if this distance is really large and the convex hull is fairly well converged and that we've sampled a lot of different states, this tells us that the system is very stable. It's very unlikely that we're going to find a system that's going to override its precedence on the convex hull, or that, let's say, other effects like entropic effects with temperature are going to override its place on the convex hull. Okay, let's talk about why this is going to be important. So we did an analysis of Heusler magnets Heusler is a particular structural type, a particular way of arranging the atoms. So here we have the three different structures of the Heusler. We have the regular structure, the inverse Heusler, and then the half Heusler. Okay, these are basically families of structures, a family of structures. It's a ternary. Okay, and what we did is we took this underlying prototype and we redecorated all the atoms with 51 different metals, elements here. Okay, so we realized a number of different candidates. Okay, possible Heusler magnets, new Heusler magnets. And in order to reduce our set down and screen for viable systems which are going to actually form, we did this thermodynamic analysis. This is one of the steps of the ways that we reduce down our set from 200 candidates to 200,000 candidates to a set that we can manage and hand to experimentalists. So one of the criteria here is we looked at the stability criterion. So we asked the question, which systems are really robustly stable? Is their stability criterion greater? Is that distance greater than 30 MeV per atom, right? This is greater than that room temperature threshold that I defined earlier. So if they're really robustly stable, we picked those out for additional analysis. And so this was one of the criteria that helped us reduce from 200,000 down to 4, okay? And of the 4, we were able to synthesize 2. And these are the experimental results for this system here, which is really robustly stable. You can see that this system is ferromagnetic, okay? And we can even tell what the Curie temperature is. It's about 950 degrees, which from additional analysis in the paper, we actually did a good job of predicting that here. And from the XRD analysis, you can see that this forms this, the system sits on this FCC structure, which is exactly how we predicted the system would form. Okay, so it did indeed form this Heusler structure that we predicted. All right, so that's another way that you can use data from the convex hull to do materials discovery. I'm going to give you one more example. So this is called the N+1 energy gain descriptor. Okay, so here we have a plot that I showed you earlier. Remember, we have the tie line here with the pure A, pure B, and then the 50-50 mixture. Okay, this distance here, I keep saying it's the driving force for the reaction, but there's another way of looking at this distance. This distance here is also the enthalpy gained from going from materials that have only one component to 2 components. Okay, so the question is, what is the energy gained from increasing the number of species, the number of elements in my material? Okay, and we can do this analysis even for higher dimensions. So instead of just asking, so now we have 3 components here, okay? And for a particular ternary, we can ask, what is the energy gain from increasing the number of species from 2 to 3, okay, or 1 or 2 to now 3 components. Okay, and we've done this analysis for all of the metals in the AFLOW database. And what we're showing here is the enthalpy gain distribution for the number of alloys for binaries, ternaries, and quaternaries. And what you can see here is that as we increase the dimensionality, we go from binaries to ternaries, you can see here that not only does the enthalpy gain decrease, but there are fewer compounds that show any enthalpy gain. And what this derives from is an important concept of this increasing competition as we increase the dimensionality of the system. So the idea here is pretty simple. If we're looking at a ternary convex hull, we need to remember that the ternary convex hull is in part made by the 3 binary convex hulls, okay? And if the binary convex hull has a really deep well here, okay, one of them or all of them have a really deep well, that's going to create more competition for the ternaries now, which now have to compete with these really stable binaries. And if we're looking at a quaternary system, they have to compete not only with the binaries, but also with the ternaries. So in order to be stable at higher numbers of compounds, you need to compete, you need to be even more lower in energy than the compositions of lower dimensionality. Okay, so that increasing composition or competition is very important. I know we didn't get the opportunity to compile AFLOW and work with the AFLOW in the terminal, but I just want to mention, I know you're going to get a copy of the slides. There are ways that you can interact with the convex hull module through the terminal that you can get a lot more properties than just what you get from the web. Okay, So I'm just going to list the commands here. We're not going to have the opportunity to try them, but you can actually query the convex hull data through the terminal. So you can get the PDF as I showed you from the web. You can get a JSON response. This is nice for integrating with Python, and a text response if you want to read things more in a tabular sense. You can get the distance to the hull for a particular entry. Okay, so if you know it's AUID, you can retrieve back exactly what the distance to the hull is. You can get its stability criterion. You can query the energy at a particular stoichiometry by providing the composition. Sorry, 1 second. By providing the composition. We have some high throughput inputs. This is not too important or relevant for our discussion here, but what I will say is that there's a big README for all these commands here if you plug in this command here to the terminal. So we haven't done this, but if you get the chance to download AFLOW and you want to play with more with these, take these slides and you'll be able to work with them using these commands. We also have a Python wrapper, which we made available. I give the URL here. And this is basically interacting with that terminal command, importing it through JSON, and then you can work with it in Python. I know a lot of people like Python, so this is one way that you can interact with the convex hull using Python. We made a nice Python wrapper. And so that's available here if you're interested in playing with those tools. You can also, this is one last way you can interact with the convex hull, you can also interact with it as a Jupyter notebook. Okay, so if you run this command here, okay, you select either Jupyter, Jupyter 3, Jupyter 2, depending on whether you have Python 3, Python 2. You can get back a Jupyter notebook and you can interact with the convex hull module through the Jupyter notebook. Okay, so we've made available a number of different ways that you can interact with our module here. Okay, so I'm going to take a quick break because we're going to go through some exercises. I'll give you a chance to run through them. All of these can be done through the web application. I'll run through the exercises very quickly, and then I'll give you, maybe we'll take 5-10 minutes and we'll run through the exercises independently, and then I'll walk you through them. Probably take about maybe 5 minutes. So the first question is, what is the distance of this particular compound from its hull? Okay. What is the stability criterion for this compound? Remember, I showed you where all these things exist in the particularly in the PDF. What is the energy of the copper zirconium hull at this particular composition, 50-50 mixture? And then what ternary compound has the highest stability criterion on this hull? Okay, so let's take a few minutes and we'll try to solve these independently, and then we'll reconvene together. And I'll also take the opportunity to answer questions if you have them. Go for it. Okay, so here you should be able to see my screen and my browser. So, oh, that's not right. Let's go to aflow.org. Let's go to the convex hull. So we know that we need to sit on this. We need to look at the results of this convex hull. So let's go to ALCO, hit submit. It should come up pretty quickly. The best way to do this, I think, is through the PDF. So you click download PDF, you open this up, and we're looking for AL17, CO12. Okay, so we're going to go to the report. And you should be able to scroll down. You can also use the finder to find the maybe 17, but I think it's just easier if I find it here. You see that it's on the second page here. It's unstable. And the distance to the hull is 243 MeV per atom. So you can see there's a very large distance to the hull, it's probably very unlikely that a system is going to be able to stabilize, let's say, through entropic contribution. So this is a very big distance, but this is the value looking for the answer here. Okay. Oh, I didn't get the chat up. Second question. So we need to go to the TEZR, convex hull. I'm just going to open up different tabs here. Going to hit, so we want to find out what the stability criterion is for this particular value. So we're going to click download PDF. We're going to open that up. This point is going to be on the hull, so we can actually trace it pretty quickly with this here. So the value we're looking for, the compound we're looking for is right here. So if I click on that, it'll bring me to that part of the report. Just a quick shortcut. And you can see that the stability criterion is 49 MeV per atom. That is this delta SC. Okay. Now that's actually pretty big, right? Relative to room temperature excitations. Okay, what is the energy of the hull at the copper zirconium hull here? So at the 50-50 concentration. So we go back to the convex hull. Type in copper zirconium. This one you can do by eye. It would be easier with the command line, but by eye it's possible to do. So you look at the 50-50 concentration, and you can see here that this point here, this is the one we're interested in. Okay, so it sits at about that point sits at about -130. The value here, roughly speaking, 150, 160. Okay, so by eye, you can actually even see it better. I think if we change, I think there's a way of changing the y-axis here. No, we want to go higher. So if you want to zoom in, you can actually change this value here. Let's see if we do 200. It's a little difficult to play with, but we should be able to do that, I think. Yeah, okay. So anyway, you can play with this a little bit by eye. It's a little difficult, but you can play with it, and you'll see that the distance to the hull is around, I think the answer is around 40 or 50 MeV per atom. Okay, but you could see what the values we were getting at. And you can also look at the PDF. The PDF might give you a little bit of a better perspective. Let's take a look. Yeah, this is a little better. So you can see here that we were looking at 130. Okay, so that sits around here. The convex hull value is at around 160, 165. Okay, so we're looking at about 30 or 40 MeV per atom. Okay, so that's the distance you're looking for roughly. If you had the command line, you would be able to get the value exactly. But that's more or less what we're looking at. Okay, and actually you should be able to get that value from the distance to the hull here. Okay, anyway, so the last question is, what is a ternary compound? Which ternary compound has the highest stability criterion on this hull? So we're going to open that up. Go to convex hull. Open up this one, hit submit. We're going to download the PDF. We're going to open that up, and you see that there are not many ternaries, and so you can see here this stability criterion is 33 MeV per atom. We should have one more. We have one that is 1 MeV per atom, and that's it for the ternaries. Okay, so the one that has the highest stability criterion is this Mn2 PDPT, and this one actually turns out to be the composition of that magnetic system that I talked about earlier. So you can see that it's higher than 30 MeV per atom, which is why we were able to find it. Okay, any questions on those questions? On those exercises? If not, I'll move on to the next part of the talk. Let me share just my slides. Okay. laser, and I have to get the chat back open. All right, I don't see any questions, so I'm going to move on. And I'm going to talk about a very, oh, there might be one. MeV per atom, please explain. Well, the energy of the distance, these are energetic values, right? And so we're looking at milli-electron volts. And the energy has been normalized by the number of atoms in the system. So you can imagine that if this is really removing the dependence on the unit cell that I use to model the system. So you can imagine that if I use a bigger cell, that the energies are just going to be bigger because there are more atoms. And so I normalize it by the number of atoms in the cell. Does that answer your question about the units there? Another commonly used normalization for formula unit. Oh, yeah, right. Okay, so I hope that answers your question here. Okay, so we're going to talk about an important correction for these energy values. So Marco talked about earlier that he referenced that there are some issues with density functional theory. And these issues in terms of calculating enthalpies seem to be most pronounced in what are called ionic materials. Ionic materials here are compounds that are formed where you mix metals with nonmetals. Okay, so they have a big difference in electronegativity. When you have these particular materials, I'll give some motivations to why there's big errors. There are big errors in their enthalpies of formation. So, okay, so first let's talk about why these are important. So ionic materials play a big role in a number of applications. They're important in batteries, the screens on your cell phone, the silicon chips inside the screens on your monitor here. They're important for the materials that go into aerospace. Okay, they offer good thermal protection, and they're important for very hard materials, like you see here, this drill bit here. So ionic materials are a very important class of materials in terms of applications. And so the fact that density functional theory does not calculate its enthalpies of formation correctly is a big problem to address, and an important one. So again, when we calculate the formation enthalpy, remember that we're taking the difference of the compound enthalpy from the reference states. Okay, so remember the pure components, pure A and pure B, we need to subtract off their enthalpies to get the enthalpy of formation of the mixture. Typically, what happens is there are errors associated with density functional theory, but a lot of these errors cancel because the reference states are similar in nature. They have a common chemical character as the compound they're forming. So for metals that decompose into metals or are made of metals, these errors are very small because of a cancellation in errors when we calculate the formation enthalpy. Remember, we're subtracting off here. So in some sense, these errors cancel out. But for ionic materials here, we actually have differences in the chemical character of the references. So the compound state here, this is some sort of ionic state. Okay, we can see that the band structure here there's a band gap, and it's made up, the reference states for these, excuse me, we have metals, okay, which have no band gap, and then we'll have something like oxygen gas, which is a molecule, which we need to look at from this perspective here. Okay, so molecules have a very different chemical character than the metals here. Okay, so there's not this nice cancellation of errors that we usually get or take for granted in the metals. Okay, and so this very different chemical character of the compound phase, which has a localization of electrons, is very different, say, than the metals, which have very delocalized electrons. So this is an explanation as to why we get these very large errors. I see that we have a question. Can the compound cesium, copper, iodine be generated from the convex hull? Sure. I don't see an issue as to why not. But this is a system which is an ionic material. And so you're going to want to consider some of these issues when you calculate, let's say, their formation enthalpies. Okay, so in terms of how to calculate the formation enthalpies from a computational perspective, we need to look at sort of, let's say, the trinity of what we're looking for. Okay, so if we want to calculate the formation enthalpies, we want this analysis to be three things. We want it to be high throughput, something that we can calculate quickly and do for a big span of different compositions. Okay, so that's what high throughput means. We want it to be accurate, and we want it to be from first principles. Okay, so something that does not, at least intrinsically, depend on empirical values or experimental values. So for metals, we can accomplish all three of these, the trinity, with semi-local density functional theory. Okay, with we have LDA, PBE, scan, these different functionals. But if we want to do it for ionic materials, there's some challenges. Okay, so we want it to be, we want it to be high throughput and ab initio. We look at, we have density functional theory, which can accomplish this. But if we want the third leg here, which is accuracy, we have some challenges there. So if we want it to be accurate and ab initio, there's some approaches here, which include exact exchange, RPA. Okay, so there's ways of doing it, but it's not going to be high throughput. Okay, so these are very expensive calculations. So if we want to complete this leg of being able to be high throughput and accurate, we need to use this method, the CCE method, the corrected enthalpies approach. Okay, so we're going to correct these enthalpies by the coordination. Okay, so why is this important? Because there are some corrections that exist in the literature which are purely dependent on just the composition. Oh, I see we have a question here. Please expand CHULL. CHULL is convex hull. I'll put that in the chat here. CHULL is equal to convex hull. Okay. Another question. What is the typical error value of a DFT and enthalpy calculation of ionic compound? Great question. I was going to show that in a few slides, but for the oxides, it can be as large as 200 MeV per atom. Okay, so you can imagine that if the point on the convex hull has an error bar, which is 200 MeV per atom, we have no sense of reliability of any analysis that's done on the convex hull. So these errors are very large, and it's very important that we correct them. So getting back to the slide, what I was going to say is that there are some corrections that exist in the literature which are only dependent on the composition of the material. Okay, they don't consider, let's say, structural aspects of the material, which include coordination. So this correction scheme we have here takes into account not only composition but also coordination. So let me give you an example of what I'm talking about here. If I'm looking at calcium oxide here, what it looks like is that we have calcium here in the middle and we have oxygen sitting around it. Okay, so it's going to be six-fold coordinated with oxygen. Okay. If we have a rutile phase of titanium oxide, we're going to have, we have a similar scenario. We have the titanium in the middle, and then we have six oxides that are coordinated around it. If we put these together and we make calcium titanium oxide, we still have coordination 6 for the titanium, but we no longer have 6 for the calcium. We have 8. So what this tells me is if I had a generic correction, which just looked at calcium and oxygen, the composition, the relative composition, this is not going to be this, it should not be the same for this composition here because we have a different coordination for the calcium. So we want a coordination scheme which is dependent on the exact coordination of how it exists in the material, okay, which really comes down to oxidation states. So what we do here, how we extract our corrections, is that we look at the differences in the enthalpies between what we calculate with density functional theory and what experiment tells us should be the right enthalpy of formation. And we extract out a correction which is dependent on the composition, the coordination, okay, and then in a particular correction for those two components. What is the composition and the coordination? And we can extract out this particular correction and we can apply it for higher order terms. Okay, so for the ternaries, for instance, we can calculate a new corrected enthalpy of formation based on our calculations and the corrections we've extracted out for the binary systems. That's how our corrections derived. And so this publication, which appeared in 2019, you can see here we have a nice table of corrections which are based on the species and its particular oxidation state, which correlates to its coordination in the material. And we derived this, so we did the corrections not only based on what its enthalpic contributions are from raw DFT, but also incorporating thermal contributions, right, vibrations. And so those corrections have been provided here in this table. I've already alluded to this, but the idea here is that we can get temperature effects. Okay, so we can get what the corrections are based on, because remember, the experiments are usually done at room temperature, and our calculations are done at zero temperature. And so we can take into account these effects. Okay, so we can get a room temperature correction and also a 0 Kelvin correction, where we subtract off the thermal contributions of the material. Okay, so basically the underlying point here is that temperature effects can be included in the corrections. So here we want to just show off some results of how this works. So you can see here that we calculate the corrections of our enthalpies of formation. So these are the CCE corrections, and we compare this to another type of correction scheme, which is called FARA there, the fitted electron reference elements or element correction. I believe that's the acronym there. It's fitted electron reference elements, I think is what it is. But so this approach basically just considers the composition. And so you can see here that if we look at the relative errors of these two approaches, you can see that the errors of CCE approaches the errors we would expect from room temperature excitations. And so it does a better job of correcting the systems relative to other schemes. We've even done this analysis, not just for the oxides, but we've looked at them for other halide systems. And so here we have, these systems have fluorine in them, they have chlorine in them. And so you can see that the corrections here, also the scheme of how we correct also applies for these systems as well. An important part of these corrections is that it's important that we not only reduce our errors, but we do so in a way that is consistent for the ordering of polymorphs. Okay, so it's not only important that you just reduce the errors, but that you reduce the errors so that the system that should be the ground state appears to be the ground state. So we did this analysis for 3 systems here where it's known, for instance, we know what the ground state should be from experiment. Okay, and we know what PBE gives us as the ground state, which is going to differ from the experiment. And we can show that for these 3 systems, especially as we use SCAN. SCAN is a particular functional. It's a little more expensive than, let's say, raw PBE, but it's going to give us better results. If we use our corrections with SCAN, we can actually recover back what the experimental ground state should be. Okay, and so even in the relative sorting of polymorphs, we can get back what we expect to be the ground state. So CCE, if we just look at the raw corrections, we can actually extract out a value, a rough value of what the formation enthalpy should be. And you can see here, so the rough values, there is an error associated with that is, let's say we don't have our calculations from which to correct our enthalpies of formation, we can still get out what's called a rough estimate of what the formation enthalpy is. Now, it has very large errors here, but the idea here is that we can actually look at what the formation enthalpy could be, even if we don't have a calculation from which to subtract it off. So the ideal scenario is that we have a DFT calculation and we have a correction for it. But even without that, we can still use CCE to get a correction just based on experiment. So now we're going to open up our web page and we're going to interact with this module through AFLOW.org. So if you navigate to this web page here, I'm gonna stop sharing in a second, and I'm going to show you how to use how to use this module just from our web page. So I'm going to close this out, stop sharing. And I'm going to share my full screen. Okay, and I opened up the chat. Okay, and I'm going to open up a new tab. Oop. You can still see my screen, right? Okay, so you navigate to AFLOW.org and you're going to go down to AFLOW Online. Okay, and I'll copy and paste this into the chat if you want a shortcut. Okay. So this web module, okay, so we've changed the example structure here, but it actually still works. But just for the sake of consistency, if you go to the next slide, if you have the deck of slides, I'm just going to copy this structure here. I think I can put this in the chat too. You can copy this structure and you can actually paste it into our example structure here. Okay. So we have magnesium oxide. Okay. And what we're going to do is that, so we input that structure here. This is where we input our structure. We're going to scroll down to the CCE section of our toolkit, and we're gonna turn on that this is the calculation we want to perform. So we're going to activate CCE. We're going to select all the functionals. I'll show you in a second what that means, and then we're just going to hit submit at the top. Okay, and you give it a few seconds, and the calculation is going to run, and we're going to look at what information we get. I'm going to blow this up so we can see what the output is. So first, it tells us what CCE detects to be the coordination that we're trying to correct. So you see here that we basically have our system where we have magnesium in the middle, and we're going to have 6 oxygen atoms around it. Okay, so if this does not match with what you expect structurally, well, then you're going to expect that the results are not going to be consistent. But in this case, this is exactly what we expect here. So it's just telling us what analysis it was done, what analysis was done based on the coordination it was able to calculate. Based on this coordination number, we can get back our oxidation numbers. Okay, so we know that magnesium is going to be a +2 oxygen state, oxygen is going to be -2, so that we have a neutral system. And then we can get the corrections. We can get corrections for both room temperature, at room temperature, and then at 0 temperature, where we subtract off the thermal contributions. We can get the correction based on MeV per cell, okay, and then MeV per atom. Okay, so these are just different ways that we've normalized the corrections, but they're basically the same correction. And then we can also get the CCE, a rough estimate of what the formation enthalpy is, just based on the experimental values that we do the corrections for CCE. Okay, so we can get a formation enthalpy and then formation enthalpy per atom. I'll show you in a second how we don't need, if we have our exact calculation, something that we did with DFT, we cannot get a rough, we can avoid getting this rough estimate, and we can actually get an exact estimate, an exact value for the formation enthalpy. So, okay, so we did that. I showed you here that we get what we get from our output. Okay, a rough guess for the formation enthalpy, just based on the experiment. Now, if you had the terminal and you downloaded AFLOW, you would be able to run this analysis from the command line. And so here we have our CCE command to get the README for all of the possible commands and the ways to use CCE from the terminal. I'm just referencing it here, but if you decide to download AFLOW, you can use these commands. You can see how you would input a particular file into CCE and how you can get back the results similar to how you do on the web page. Okay, you can get back the same results that we have on the web page. And you can even select particular functionals. Let's say you didn't want it for all the functionals, but you wanted to just a particular functional. And then you can also input, if you've already done the calculation and gotten the formation enthalpies from DFT, you can actually give it as an input. And then instead of getting a rough estimate of the formation enthalpy, you can get an exact formation enthalpy, or exact to within our correction here. And you can also provide the oxidation numbers for the atoms. Let's say if CCE did not calculate the oxidation numbers correctly for you. So you can actually force CCE to do it for a particular coordination. Okay, so we're going to wrap up here with just some exercises. So I give you a number of structures here. I don't know if you have the deck of slides with you, if you've been able to, if it's been provided for you, because if it has, then you have the three structures that we're going to use for the exercises, but I'm going to copy it to the chat anyway. So that's structure number 1 for problem number 1. This is structure number 2. And then structure number 3. It's too big. I can't paste it. Let's see. You guys have the slides, right? You can actually get this and copy and paste it from the PDF. Does everyone have the slides? Because if you do it, then you'll be able to grab it from there. All right. So yes, the record. I don't know if the recordings from yesterday's lecture have been made available, but they will be soon. Okay, so let me walk through the exercises, and then you can go ahead and run the exercises based on these 3 structures here. So first, what is the oxidation numbers that the CCE algorithm calculates for the first structure? Okay, so you're going to take that structure, you're going to run it into CCE and get what are the oxidation numbers. You're going to figure out what is the functional that has the largest correction for given structure number 2 at room temperature. And then what are the corrections given that we provide you the DFT calculated formation enthalpies. So I give it to you for PBE, for LDA, and for scan. Use this as an input to get the exact formation enthalpies. Okay. And we can take 5 minutes here and do these exercises, and then I'll walk you through the answers. Okay, so let's get back to solving these exercises. So first question, what oxidation numbers does the algorithm provide for this structure? So I'm going to take this structure, copy, paste it here, paste it here. Looks okay, and I'm going to scroll down to CCE. Okay, and I should hit submit. Let's see if it pops up. Okay, so the coordination numbers you see here are so you see that for molybdenum we get +6. For oxygen, we get -2, so that's expected. And then for lead, we get +2. And there's this question of which one do we pick to be the +6, which one do we pick to be the -2? And this question has to be answered with the relative electronegativities of these systems. Okay, so we do an analysis of which system has a lower electronegativity, which one's going to be electron hungry. And that's going to be the system that we assign, that's the way that we assign the oxidation states here. Okay. So, that's the important piece here. Okay. The next piece is what functional has the largest CCE correction for this system at 200 at room temperature. So I'm going to take this structure, copy. Top. Delete, paste, and I should be able to scroll down. So hit submit. Question is which one has the largest CC correction at 200? Okay, so if we look at just the 200, the room temperature corrections. So PBE has for per cell is +1.6, LDA has -2.4. and scan has -1.6. So you can see that the largest is LDA, okay, at room temperature. All right, that's how you read those results. Finally, this analysis here, this is another good one because we're going to put in more parameters. So I'm going to delete this output. I'm going to paste in the structure. And what it's telling me here is I want to actually calculate the formation enthalpies, not just the corrections. Okay, so it's going to give me, we need to calculate what the formation enthalpies are of DT, provide them as an input to the algorithm so that it can correct them and give me the final corrected formation enthalpy. So we're going to scroll down. and we're going to provide the formation enthalpy. So I'm going to click on that little tab there, and I'm going to provide these values in order. Okay, so for PBE, we get this value. For LDA, I'm going to get this value. And for scan, I get this value. And I'm going to hit submit. And you can see here that the formation enthalpies here are provided. Okay, so we can see that we'd ask for formation enthalpies at PBE, LDA, and scan for the perovskite at 0 temperature. Okay, so at 0 temperature, this is the value we're looking for. Okay, these values. For LDA, these are the values. And then for scan, these are the values. Any questions at all about the lecture, about these exercises? I'm happy to answer. But otherwise, that wraps up our session for today. And I thank you for your time.